Okay, thank you. Good afternoon. I'm pleased to present you this talk concerning the integration of HTS, high temperature superconductors, as in electrical machines as armature windings in electric machines. It's a part of a PhD thesis of the PhD thesis of Yazid Statra in the electrical in the research group in electrical energy of Nancy. Okay, no problem. And in this case, the tested sample is fed by an alternating current source, and the measurement involves a more elaborate apparatus using synchronous detection. A coil, which is the which is the basic structure of the electrical machine, HTS electrical machine, is characterized in different configuration, in self-field or in presence of other coils, permanent magnets, and in the proximity of iron cores, ferromagnetic materials, to characterize the effects of this proximity of these active electrically and magnetically active materials on the performance of the HTS cores, which is illustrated in these figures. To extract the iron cores, the iron losses in the measurement, a copper coil is used. We use a copper coil of the same structure, of the same size as the HTS coil, and we measure the losses using this HTS coil, copper coil. And then, as the copper coil is not affected, as the joule losses in the copper coil is not affected by the magnetic field, we can extract the iron losses from the copper coil measurement. And then, as the copper coil has the same structure and produces the same magnetic field, and in the same condition, we can say that this is the iron losses using the HTS coil. This technique was previously published by Professor Amelia and used in this work. Okay, so to test the performance of this modeling or this developed theoretically and experimentally tools for the characterization, we have built a prototype, an axial field synchronous machine containing a rotor, for which the rotor is constituted of permanent magnet mounted on an iron plate, and the stator is a three-phase stator containing three HTS cores mounted on a laminated iron core. The size of the prototype or specification of a prototype are given here and may be consulted further in the presentation. The experimental setup is shown here. The armature of the HTS machine is put inside a cryogenic enclosure, and the rotor is put in the room temperature, driven by an asynchronous motor at different speed. The asynchronous motor is controlled by power electronics, and there are some measurement apparatus of the signals, voltage and currents. The coils were characterized using separately characterized to check whether they are the same or not. They have the same behavior, and the critical current inside the coil is also determined. This time determined by modeling, by simulation, with respect to the internal angle. That means with the rotation of the rotor, with respect to the HTS coils. Preliminary tests show good preliminary tests in generator mode gave this result. So we have this here the voltage in the coils, the obtained voltage with the rotation at 600 RPM, the evolution of the RMS of this voltage with respect to the frequency. This means the frequency is directly linked to the rotating speed. The static torque measured and computed. There is a slight difference between the computed and measured static torque. This is mainly due to the variation of the air gap of the machine with the rotation of the coils, which was not mastered. Here we have the evolution of the voltage with the load, the RMS current considering a resistive load obtained by modeling and experimental. So the result, preliminary results are rather conclusive. I go to the conclusion. Here we have developed some tools to characterize HTS element from HTS fully HTS machine from the element to the system. The preliminary results are rather conclusive, but some attention has to be paid in these systems. We have destroyed in our experimental procedure, we have destroyed the HTS cord due to the concentration of nitrogen gas in these regions. So the HTS cords have been destroyed. Some issues remains in such work. This work is mainly the polyphase loss measurement. Could not measure using the electrical method. We could not measure the polyphase AC losses. We have just measured each coil separately, the losses in each coil separately, and not in rotating magnetic field. And the losses in the prototype in the system. Professor Min presented a way to measure these losses by considering the evaporation of liquid helium or nitrogen. I didn't get to the gas she used. By here, we want to measure the instantaneous losses. We could not measure them by the electrical method. So works are carried out to overcome this or to give solution to these issues. And this is the end of my talk. Thank you for your attention.
Otherwise, there is one question from Professor Nakamura.
Yeah.
He said, "Thank you for the presentation." So you can read here.
Thank you. Read.
Yes.
I can see the.
Okay. AC losses considering the analysis, HTS armature windings. He is asking where is located the AC losses in your systems.
The AC losses are in the armature windings and in the iron core supporting the armature windings. So we have ferromagnetic losses, iron losses, and the same equivalent losses in the superconductor. So both are put in the cryogenic enclosure, and the evolution of both losses is important to size the cryogenic parts of the machine.
And related to this question, when you measure the losses, is there the losses from the iron are included in the measurements, or just measure the losses for the tapes?
Yeah, in separated measurements, we include the iron losses by the method we presented to separate the iron losses from the HTS IC losses includes this part. But they are measured separately for each coil and not when feeding all the coils together. Not in rotating magnetic field, but in pulsed magnetic field, if we can say. With the assumption that the coils are the distance between the coils is quite large, and the connection or the interaction between the coils is can be neglected in this case.
Okay.